Right now, 3,000 kilometers beneath South America, deep within the churning heart of our planet, Earth's magnetic shield is turning against itself in ways we're only beginning to comprehend. The South Atlantic Anomaly, a zone of weakness that used to be a mere curiosity for scientists, has doubled in size over the past decade and is now splitting into two separate lobes. Satellites crossing this region experience glitches and unexplained malfunctions. Astronauts shelter in reinforced modules when passing overhead, and deep in Earth's core, reverse flux patches are doing something that shouldn't be possible according to our models, forcing magnetic field lines to plunge back inward, cancelling our defenses from the inside out. Meanwhile, the North Magnetic Pole is racing towards Siberia, faster than ever recorded in human history, and the sun just hit solar maximum. Something fundamental is changing beneath our feet, and we're only beginning to understand what it means for our technological civilization. Stay with me, because by the end you'll discover why scientists are calling this a cosmic emergency that could reshape our technological future in profound ways. If you're as intrigued by these unfolding magnetic mysteries as I am, consider subscribing so you can follow along as scientists track these changes happening right now. Leave a comment letting me know where you're watching from, what time zone you're in, and what you think about these planetary scale shifts we're witnessing together in real time. Part 1. The shield is changing before our eyes. Something is profoundly wrong with Earth's magnetic field, and it's happening faster than anyone expected or predicted. Right now, as you listen to this, satellites are threading through a zone of weakness stretching across South America and the South Atlantic Ocean. This zone, officially called the South Atlantic Anomaly, has been growing, not slowly, not imperceptibly, but dramatically, measurably, alarmingly. In the span of just a decade, this magnetic dent has expanded to cover an area roughly half the size of continental Europe. Imagine a shield that has protected our planet for billions of years, suddenly developing a crack that keeps widening year after year, and you start to understand why scientists are no longer treating this as a curiosity. The South Atlantic Anomaly was always there, lurking in our data, a known quirk of the geomagnetic field that engineers designed around. Satellite operators knew to expect a few glitches when their spacecraft crossed this region. Astronauts on the International Space Station would close the shutters on certain modules when passing overhead, a routine precaution. It was manageable, it was predictable, it was stable. But stability, it turns out, was an illusion we told ourselves while the numbers quietly shifted beneath our feet. Data from the European Space Agency's Swarm satellite constellation tells a different story now. These three identical satellites, launched in 2013 to map Earth's magnetic field with unprecedented precision, have been watching the anomaly morph in real time. What they've discovered should concern anyone who relies on technology, which in 2026 means essentially everyone on the planet. The South Atlantic Anomaly isn't just expanding, it's splitting. Where there was once a single depression in magnetic field strength, there are now two distinct lobes, one centered over South America and another developing southwest of Africa. The field isn't weakening uniformly, as we might expect. It's reorganizing, restructuring, doing something we don't fully understand. Beneath these weak zones, something even stranger is happening. Scientists have identified what they call reverse flux patches, regions where the magnetic field lines, instead of radiating outward from Earth's core like they're supposed to, loop back downward and plunge into the planet. Imagine trying to inflate a balloon while someone pokes holes in it from the inside. That's essentially what these reverse flux patches are doing to our magnetic shield. They're cancelling out the protective field from within, creating vulnerabilities that didn't exist before. Meanwhile, on the opposite end of the planet, the North Magnetic Pole has been racing across the Arctic at speeds that would have seemed impossible to 19th century explorers who first attempted to locate it. For most of recorded history, the pole wandered lazily, drifting a few kilometers per year at most. Then, around the turn of the millennium, it started accelerating. By 2020, it was covering more than 50 kilometers annually, barreling from Canadian territory towards Siberia, like it had somewhere urgent to be. As of 2025, it shows no signs of slowing down. This isn't abstract geophysics happening in some theoretical model. This is measurable, trackable change occurring within a single human lifetime. The World Magnetic Model, the system that underpins every compass, every GPS device, every navigation system on the planet, had to issue an emergency update in 2019 because the pole had moved so far that the model's predictions were no longer accurate. That update was supposed to last until 2025. It barely made it. The timing couldn't be worse. While Earth's magnetic shield shows signs of structural instability, The Sun is entering solar maximum, the peak of its 11-year activity cycle. Solar maximum means more sunspots, more solar flares, more coronal mass ejections, hurling billions of tons of charged particles toward Earth. Under normal circumstances, our magnetosphere would deflect most of this radiation, channeling it safely around the planet. But normal circumstances assume a robust, stable magnetic field. What we have now is a shield with a growing hole in it, and the bombardment is intensifying. This convergence raises questions that keep geophysicists awake at night. Is the South Atlantic anomaly a temporary fluctuation, or is it a symptom of something fundamental changing in Earth's core? Are we witnessing the early stages of a geomagnetic excursion, one of those rare events where the magnetic poles temporarily wander or even swap positions? Could this be the beginning of a full polarity reversal, the kind that takes thousands of years to complete but leaves the planet vulnerable throughout the transition? Or is this something else entirely? A behavior we haven't observed before because we've only had precise instruments for a few decades. The magnetic field isn't just some abstract force that occasionally makes compasses point north. It's a critical infrastructure system, arguably the most important one we never think about. It shields us from solar radiation that would otherwise strip away our atmosphere the way it stripped away Mars's atmosphere billions of years ago. It protects the satellites that enable global communication, weather forecasting, financial transactions, military operations, and the navigation systems that guide ships and aircraft. It reduces the radiation exposure of astronauts and airline passengers flying at high altitudes. It's been doing this job reliably for 4 billion years, and we've taken it completely for granted. Now, for the first time in human history, we have the instruments to watch it change in real time. And what we're seeing suggests that change might be accelerating. The South Atlantic anomaly that was merely interesting in 2014 has become urgent in 2026. The pole movement that was academic curiosity has become a navigation problem. The reverse flux patches that were theoretical constructs have become measurable realities, undermining our shield from within. So, what exactly is this anomaly doing, and why is its behavior becoming stranger rather than stabilizing? To understand that, we need to look more closely at what's happening beneath South America and the South Atlantic, where Earth's magnetic defenses are quietly falling apart. Part 2. Anatomy of the anomaly beyond simple weakening. The South Atlantic anomaly doesn't look like much on a map until you understand what you're seeing. Standard visualizations of Earth's magnetic field show a relatively smooth dipolar structure, strongest near the poles and weakening slightly toward the equator. Exactly what you'd expect from a giant bar magnet buried inside the planet. Then you zoom in on the region between South America and Southern Africa, and the smooth pattern breaks down completely. The field strength plummets, where the global average hovers around 30,000 to 60,000 nanoteslas. The South Atlantic anomaly dips below 25,000 nanoteslas and keeps falling in localized pockets. It's as if someone carved a depression into the magnetic landscape, a valley where the shield grows dangerously thin. This weakness has consequences that become visceral when you're in orbit. The magnetosphere normally forces charged particles from space into two distinct radiation belts, the Van Allen belts, which surround Earth like enormous donuts of concentrated radiation. These belts are mostly stable and predictable. Satellite designers know where they are and plan accordingly. But over the South Atlantic anomaly, the inner Van Allen belt sags closer to Earth, dipping down toward the altitude where satellites and the International Space Station orbit. Suddenly, spacecraft that should be safely below the worst radiation find themselves swimming through it instead. The European Space Agency's Swarm mission wasn't looking for problems when it launched in 2013. The constellation was designed to map magnetic field variations with extraordinary precision, tracking changes down to timescales of weeks rather than years or decades. What Swarm found was unsettling. The South Atlantic anomaly wasn't behaving like a simple static weak spot. It was dynamic, complex, almost organic in how it shifted and evolved. The satellites revealed a structure far more intricate than scientists had anticipated, with subregions that weakened at different rates, boundaries that expanded and contracted, and internal features that appeared, merged, and separated over time. By 2020, swarm data showed the anomaly wasn't just growing, it was splitting into two distinct lobes. One lobe centered itself over southeastern South America, extending from southern Brazil down through Uruguay and Argentina. The other developed thousands of kilometers to the east, hovering over the South Atlantic Ocean southwest of Africa. Between these two lobes, the field strength showed slightly more resistance, creating a saddle-shaped structure that defied the simple narrative of uniform weakening. This wasn't a shield developing a single crack. This was a shield developing a complex fracture pattern, the kind of structural failure that suggests deeper problems. The swarm satellites also detected something that shouldn't exist in a healthy magnetic field: reverse flux patches. In a normal magnetic field lines emerge from Earth's interior, arc through space in elegant loops, and eventually re-enter the planet on the opposite side. The field flows outward from the southern hemisphere, sweeps around the planet, and flows back inward near the northern hemisphere. Clean, orderly, protective. But reverse flux patches disrupt this flow. They're regions where field lines, instead of radiating outward, immediately loop back downward and plunge into Earth's core. It's as if the core itself is trying to swallow its own magnetic field. These reverse flux patches appear directly beneath the South Atlantic Anomaly. They're not surface phenomena. They originate deep in the outer core, 3,000 kilometers below South America and the South Atlantic. At that depth, liquid iron rotates and convects, generating Earth's magnetic field through a process called the geodynamo. When the flow patterns in this liquid iron change, the magnetic field at the surface changes too. Reverse flux patches suggest the flow patterns down there are doing something unusual, creating upwellings or eddies or vortices that produce backward-pointing field lines. The field isn't just weakening, it's reversing polarity in localized regions. The geography of the anomaly matters more than you might think. South America and the South Atlantic sit atop one of the most geophysically complex regions on Earth. The core mantle boundary, the interface between the liquid iron outer core and the rocky mantle above it, is not uniform. Beneath Africa, seismic studies reveal a massive low shear velocity province, a continent-sized blob of unusually hot material sitting at the base of the mantle. This blob influences heat flow between the core and mantle, which in turn influences convection patterns in the liquid iron. Some researchers suspect the African blob might be connected to the South Atlantic Anomaly's formation and evolution, though the exact mechanism remains debated. What scientists do agree on is that the anomaly reflects processes happening in the outer core. Earth's magnetic field is generated by the motion of conductive liquid iron in a spherical shell, roughly 2,000 kilometers thick, rotating around a solid inner core. This motion is driven by heat escaping from the core, by compositional buoyancy as lighter elements separate from heavier ones, and by the Coriolis effect imparted by Earth's rotation. It's a turbulent, chaotic system, and small changes in flow can amplify into large changes in the magnetic field over decades or centuries. The swarm satellites measure these changes by detecting tiny variations in magnetic intensity as they orbit. Ground-based observatories provide complementary data, tracking long-term trends and offering baselines that extend back more than a century. Together, these measurements feed into models like the International Geomagnetic Reference Field, which attempts to describe Earth's magnetic field mathematically using spherical harmonics. The models work mostly, but they require constant updating because the field refuses to stay still. Every 5 years, scientists release a new version of the model, adjusting coefficients and adding correction terms to account for how the field has shifted since the previous version. The South Atlantic Anomaly's splitting behavior is particularly troubling because it suggests the underlying flow patterns in the core are reorganizing in ways the models didn't predict. If the anomaly was simply weakening uniformly, that would be one thing. But the development of two distinct lobes, the appearance of reverse flux patches, the accelerating expansion rate, all of these point toward a fundamental restructuring of the geodynamo rather than a minor fluctuation. It's the difference between a small crack in a dam and a structural defect that could propagate. So, we have a shield that's not just thinning, but tearing in complex ways, driven by processes we can observe, but not yet fully explain. The natural question becomes, how unusual is this? Has Earth's magnetic field done this before? And if so, what happened next? To answer that, we need to step back and look at the bigger picture of magnetic pole movement and what it tells us about the stability of our planetary defenses. Part 3. Pole drift versus narrative drift. What's real and what's hyped? Earth's magnetic poles have always moved, and that's important to understand before panic sets in. The North Magnetic Pole, the point where magnetic field lines point straight down into the planet, is not the same as the geographic North Pole. It never has been. The magnetic pole wanders because the liquid iron currents that generate it are constantly shifting. For most of human history, this wandering was slow enough to ignore. Early European explorers who ventured into the Arctic with compasses didn't worry much about the magnetic pole's exact location because it stayed in roughly the same neighborhood for their entire lifetimes. Cartographers could mark it on a map, and that map would remain useful for generations. Then, in the late 20th century, the wandering accelerated. By the 1990 seconds, the pole was moving noticeably faster than historical norms, tracking across the Canadian Arctic at about 15 kilometers per year. By 2010, that speed had tripled to more than 40 kilometers annually. By 2020, it was covering more than 50 kilometers per year, racing northeast towards Siberia with no signs of slowing down. This acceleration caught scientists off guard. Nothing in the historical record suggested the pole should be moving this fast. The movement is real. It's measured by satellites, confirmed by ground observations, and incorporated into navigation models worldwide. The World Magnetic Model, maintained jointly by the National Oceanic and Atmospheric Administration and the British Geological Survey, tracks the pole's position and predicts where it will be in the near future. This model underpins every GPS device, every smartphone compass, every aircraft navigation system. When the model's predictions start diverging from reality, problems emerge quickly. In 2019, the model failed ahead of schedule. It was supposed to remain accurate until 2020, but the pole's accelerating movement made it obsolete early. Engineers issued an emergency update, recalculating the magnetic field coefficients to match the pole's new position. That emergency update was unusual. It signaled that something about the core's behavior had changed enough to break the model's predictive assumptions. Now, here's where narrative drift starts corrupting the story. Social media and certain corners of the internet have seized on the pole's movement as evidence of an imminent catastrophe, a sign that Earth's magnetic field is about to collapse or reverse within years. Some posts claim the poles could flip completely by 2030, plunging civilization into chaos as compasses spin wildly and radiation pours through a failing magnetosphere. These claims are not supported by evidence. They are extrapolations built on misunderstandings of how geomagnetic reversals work. Reversals do happen. Earth's magnetic field has flipped polarity hundreds of times over the past billion years, with magnetic north becoming magnetic south and vice versa. The geological record preserved in volcanic rocks and seafloor sediments shows these events clearly. When lava cools, magnetic minerals within it align with Earth's field, freezing a snapshot of the field's direction at that moment. By studying ancient lava flows, scientists can reconstruct the history of magnetic reversals going back millions of years. What this record shows is that reversals are slow. They don't happen overnight or even over decades. A typical reversal takes anywhere from 1,000 to 10,000 years to complete. During that time, the field doesn't disappear. It weakens, becomes more complex, develops multiple poles, wanders chaotically, and eventually settles into a new stable configuration with reversed polarity. Life doesn't end during reversals. Extinctions don't correlate with reversal timing. The field remains strong enough to provide some protection even during the transition. There's another category of events called geomagnetic excursions, where the poles temporarily shift or wander significantly before returning to their original configuration without completing a full reversal. The Lachamp event, which occurred around 41,000 years ago, is the most famous example. During the Lachamp, the magnetic field weakened dramatically, dropping to about 25% of its normal strength, and the poles wandered toward the equator before eventually returning north and south. The event lasted about 1,000 years. Life continued. Humans survived. The field recovered. The South Atlantic Anomaly and the racing North Magnetic Pole are interesting, yes, but they don't prove a reversal is imminent. The field's overall strength has been declining for the past 2,000 years, dropping about 9% over that time. That sounds dramatic, until you realize 9% over 2 millennia is a gradual change, not a collapse. The field has been stronger and weaker than it is now at various points in the past without triggering reversals. What scientists do find intriguing is the combination of factors: the weakening field, the expanding anomaly, the accelerating pole movement, and the complex internal structure revealed by SWARM. Taken together, these suggest the geodynamo might be in a transitional state, shifting from one mode of operation to another. Whether that transition leads to an excursion, a reversal, or simply a temporary wobble before stabilizing again remains unknown. The data doesn't support confident predictions on decade timescales. Narrative drift happens because humans crave certainty and drama. A story about poles drifting slightly faster than usual doesn't capture attention the way a story about imminent magnetic apocalypse does. So the facts get stretched, the timelines get compressed, and suddenly you have viral posts claiming civilization will collapse when the poles flip in 5 years. Those posts ignore the science, dismiss the historical record, and confuse pole movement with field collapse. The International Geomagnetic Reference Field, updated every 5 years, incorporates current pole positions and field variations. The model assumes the field will continue changing at roughly its current rate, which is a reasonable assumption given the historical data. If something dramatic were about to happen, we'd expect to see accelerating changes across multiple metrics. So far, we don't. The changes are significant, yes, but not catastrophic. Still, the anomaly's growth and the pole's acceleration are real phenomena driven by real changes in Earth's core. Dismissing them as non-issues would be equally irresponsible as hyping them into apocalypse narratives. The truth sits in the middle. Something is changing. We're monitoring it closely. We don't know where it's headed, but we're watching every data point to find out. And while we watch the poles and the anomaly, there's another consequence of these changes that's already causing problems. Something concrete and measurable happening right now in the technology we depend on daily. Satellites are feeling the effects, and their operators are starting to worry. Part 4. Tech Threat. How the SAA is already hurting satellites. Satellites crossing the South Atlantic Anomaly don't announce their suffering with alarms or warning lights, but the damage accumulates quietly in their circuits. Every satellite in low Earth orbit eventually passes through the anomaly. There's no avoiding it. Orbital mechanics dictate the path, and that path includes regular transits over South America and the South Atlantic. For most satellites, this means exposure to radiation levels significantly higher than they experience anywhere else in their orbit. The Van Allen radiation belts, normally held at bay by the magnetosphere, sag down through the weakened field and bathe spacecraft in charged particles that would otherwise be deflected safely away. These particles, mostly high-energy protons and electrons, accelerated by solar wind and trapped in Earth's magnetic field, penetrate satellite hulls and interact with electronics. When a high-energy particle strikes a transistor or memory cell, it can flip bits, corrupt data, or cause what engineers call single-event upsets. A single-event upset sounds minor, almost trivial, until you realize modern satellites rely on millions of transistors working correctly in concert. One flip bit in the wrong place at the wrong time can crash a computer, corrupt a command sequence, or force a satellite into safe mode. Spacecraft operators have been dealing with single-event upsets for decades, but the South Atlantic Anomaly has made the problem worse. As the anomaly expands and intensifies, the radiation dose satellites receive during each transit increases. Engineers design redundancy into critical systems using error-correcting memory and radiation-hardened components, but there are limits to how much protection is practical. Hardened components are expensive, heavy, and often less capable than their commercial counterparts. Every kilogram of shielding is a kilogram that could have been scientific instruments or fuel. Trade-offs are inevitable. The International Space Station experiences the South Atlantic Anomaly about half a dozen times per day as it circles Earth every 90 minutes. When the station approaches the anomaly, astronauts know to avoid certain modules. The most heavily shielded areas are marked safe, while modules with thinner walls or sensitive equipment are temporarily off-limits. Astronauts don't receive dangerous radiation doses from brief transits, but the cumulative exposure adds up over months-long missions. Radiation dosimeters track every millisievert, and mission planners carefully monitor totals to ensure crew members don't exceed safety limits. For automated satellites, the strategy is different. Some operators power down sensitive instruments during anomaly transits, reducing the chance of upset events. Others rely on onboard computers to detect and correct errors in real time, a constant game of catch-up as particles bombard the systems. A few satellites have failed catastrophically after particularly intense radiation hits, though distinguishing natural hardware failures from radiation-induced ones can be difficult post-mortem. The economic implications are substantial. Satellite failures cost millions of dollars, sometimes hundreds of millions, when you factor in lost capability, replacement launches, and insurance claims. Communication satellites enable global internet connectivity. GPS satellites enable navigation for billions of devices. Weather satellites enable storm forecasting and climate monitoring. Earth observation satellites enable agriculture, disaster response, and environmental tracking. When any of these systems degrade or fail, the ripple effects touch industries and lives worldwide. GPS accuracy depends on precise timing signals from satellites overhead. Radiation-induced errors in satellite clocks or positioning data propagate through the system, creating temporary glitches or positional errors. Most users never notice because redundancy and error correction handle minor problems automatically. But large-scale disruptions remain possible if multiple satellites experience upsets simultaneously during strong space weather events. NASA tracks South Atlantic Anomaly effects carefully, publishing studies on radiation exposure, satellite anomalies, and mitigation strategies. The data shows unambiguous trends. Satellites crossing the anomaly experience more upsets than satellites at similar altitudes elsewhere. The number of upsets per transit has been increasing as the anomaly expands. Some spacecraft now require more frequent software resets or protective mode activations than they did a decade ago. Engineers respond by designing newer satellites with more robust electronics, better shielding, and improved error detection. But these improvements add cost and complexity, and they can't eliminate the problem entirely. As long as the anomaly persists and grows, satellites will remain vulnerable. The space industry is also watching the anomaly because it complicates future plans. Mega constellations of thousands of small satellites in low Earth orbit are being deployed by multiple companies to provide global internet coverage. Each of these satellites will cross the South Atlantic Anomaly regularly, potentially dozens of times per day depending on orbital configuration. Multiply thousands of satellites by thousands of transits, and the cumulative radiation exposure becomes a significant design constraint. Failures that might be rare for individual satellites become statistically inevitable across large constellations. Human spaceflight beyond low Earth orbit faces similar challenges. Missions to the Moon or Mars spend time in regions where Earth's magnetosphere provides minimal protection. Astronauts on these missions receive higher radiation doses than those on the International Space Station, and mission planners must account for solar activity, cosmic rays, and occasional solar storms. If Earth's magnetic field continues weakening, even low Earth orbit could become more hazardous, raising the bar for long-duration missions and potentially limiting crew rotation schedules. Some researchers have proposed active shielding concepts using electromagnetic fields to deflect charged particles, essentially creating artificial mini-magnetospheres around spacecraft. These ideas remain mostly theoretical, limited by power requirements and engineering challenges, but the South Atlantic Anomaly's growth is making them seem less like science fiction and more like eventual necessity. The satellite problems are not hypothetical or distant future concerns. They're happening now, affecting operational spacecraft, and gradually getting worse as the anomaly expands. Engineers are coping, adapting, building more robust systems, but there's an uncomfortable question lurking beneath the technical responses. If a localized weakness in Earth's magnetic field can cause this much trouble, what happens if the field weakens globally during an excursion or reversal? And what if that weakening coincides with increased solar activity, the very situation we're entering right now? Part 5. Space Weather Context. Solar maximum isn't helping. The sun doesn't care about Earth's magnetic problems, and right now, the sun is getting violent. Solar maximum, the peak of the sun's roughly 11-year activity cycle, arrived in 2024 and is expected to continue through much of 2025 and into 2026. During solar maximum, the sun's magnetic field becomes tangled and complex, producing more sunspots, more solar flares, and more coronal mass ejections. These events hurl massive clouds of charged particles toward Earth at speeds approaching 1,000 kilometers per second. When they arrive, typically 1 to 3 days after launch, they collide with Earth's magnetosphere and trigger geomagnetic storms. Under normal circumstances, Earth's magnetosphere handles this bombardment well. The bow shock, the boundary where the magnetosphere meets the solar wind, deflects most particles around the planet. Field lines stretch and compress. Auroras light up the polar skies, and sensitive instruments measure fluctuations, but the overall system remains stable. Life on the surface barely notices. But circumstances aren't entirely normal anymore. The South Atlantic Anomaly represents a localized failure in the shield, a region where the magnetosphere's defenses are compromised. During geomagnetic storms, this weakness becomes more pronounced. Charged particles that would normally be deflected find easier paths through the anomaly, penetrating deeper into the atmosphere and reaching satellite altitudes more readily. The combination of solar maximum and a weakening magnetic field creates a perfect storm scenario for space technology. Solar activity follows predictable patterns more or less. Every 11 years or so, the sun transitions from solar minimum, when sunspots are rare and activity is low, to solar maximum, when the solar surface becomes chaotic and energetic. The current cycle, solar cycle 25, began around 2019 and is expected to peak sometime between 2024 and 2026. Predictions are imprecise because the sun doesn't follow a strict schedule, but the trends are clear. Activity is increasing, and we're entering the most dangerous period of the cycle. Recent data from solar observatories confirms the trend. Sunspot numbers are climbing. Solar flares are occurring more frequently. X-class flares, the most powerful category, are being recorded multiple times per month, each one releasing energy equivalent to billions of megatons of TNT. Coronal mass ejections follow many of these flares, ejecting billions of tons of plasma into interplanetary space. Some of these ejections are aimed directly at Earth. When a coronal mass ejection strikes Earth's magnetosphere, the impact creates a geomagnetic storm. Storm intensity is classified on a G scale from G1 minor to G5 extreme. G1 storms cause minor fluctuations, beautiful auroras at high latitudes, and occasional GPS accuracy reductions. G5 storms, rare but devastating, can collapse power grids, disable satellites permanently, and generate auroras visible at equatorial latitudes. The infamous Carrington event of 1859, the most powerful geomagnetic storm in recorded history, would likely rank as a G5 or beyond. Telegraph systems worldwide failed, auroras appeared as far south as the Caribbean, and compass needles swung wildly. If a Carrington-class event occurred today, the economic damage could reach trillions of dollars. The South Atlantic Anomaly doesn't directly cause geomagnetic storms, but it amplifies their effects in localized regions. Satellites crossing the anomaly during a storm receive double exposure, first from the storm's enhanced radiation belts, and second from the anomaly's weakened shielding. Astronauts on the International Space Station must sometimes shelter in the most protected modules during severe storms, adding South Atlantic Anomaly transits to their risk calculations. Ground-based infrastructure can also be affected, though the mechanisms are less direct. Geomagnetic storms induce currents in long conductors like power lines and pipelines. These geomagnetically induced currents can overload transformers, causing blackouts that cascade across electrical grids. The Quebec blackout of 1989, triggered by a moderate geomagnetic storm, left 6 million people without power for hours. More severe storms could cause damage requiring months to repair, particularly if multiple transformers fail simultaneously. Airlines flying polar routes face additional radiation exposure during geomagnetic storms. Commercial aircraft cruise at altitudes where Earth's atmosphere provides some shielding, but that shielding diminishes near the poles where magnetic field lines converge. During intense storms, airlines sometimes reroute flights to lower latitudes to reduce crew and passenger radiation doses. If the magnetic field continues weakening, these precautions might become more frequent or extend to routes that currently operate without concern. Space weather forecasting has improved dramatically over the past few decades. Satellites like the Deep Space Climate Observatory sit at the L1 Lagrange point about 1.5 million kilometers sunward of Earth, providing early warning when coronal mass ejections are incoming. Ground-based observatories monitor solar activity constantly, watching for flares and eruptions that might pose threats. Models predict storm intensity and arrival times with increasing accuracy, though surprises still happen. The National Oceanic and Atmospheric Administration Space Weather Prediction Center issues alerts when significant activity is detected, giving satellite operators, power grid managers, and airlines time to prepare. These warnings save money and potentially lives, but they can't eliminate the threat entirely. Protection requires either shutting down vulnerable systems temporarily, which has economic costs, or accepting the risk, which has technological costs. The convergence of solar maximum and the expanding South Atlantic Anomaly creates a vulnerability window that will persist for several years. As solar activity peaks, Earth's weakened magnetic field will be tested repeatedly by coronal mass ejections and solar flares. Each test provides data on how the system responds, but each test also carries risk of damage or failure. We're essentially running a planetary-scale experiment, and the results won't be fully known until the cycle completes. But while engineers and scientists worry about satellites and power grids, a deeper question nags at geophysicists studying the South Atlantic Anomaly's internal structure. What if the anomaly isn't just a surface phenomenon? What if it's telling us something fundamental about what's happening in Earth's core, something connected to processes we're only beginning to understand? Part 6. Reverse flux patches. Tip of the core iceberg. 3,000 kilometers beneath South America, Earth's magnetic field is turning against itself. Reverse flux patches are not intuitive phenomena. In a healthy magnetic field, field lines emerge from one hemisphere, arc through space, and re-enter the planet in the opposite hemisphere. The field flows outward, creating a protective bubble that deflects solar wind and traps radiation in organized belts. This is the dipole configuration, the bar magnet model we learn in school, and it describes Earth's field reasonably well most of the time. But magnetic fields can be more complex than simple dipoles. They can have quadrupole components where 4 poles emerge instead of 2, or octopole components with 8 poles, or even more exotic multipole structures. Earth's field contains all of these higher-order components, usually weak compared to the dominant dipole, but present nonetheless. Reverse flux patches are manifestations of these higher-order components becoming locally stronger, creating regions where the field direction flips relative to the surrounding area. Imagine standing on the surface with a compass. Normally, the needle points roughly north, aligning with the magnetic field lines emerging from Earth's interior. But place that compass over a reverse flux patch, and the needle might point downward, following field lines that plunge back into the planet instead of radiating outward. The field hasn't disappeared. It's reversed direction, creating a localized magnetic south pole in the middle of what should be the northern hemisphere. Swarm satellites have mapped multiple reverse flux patches beneath the South Atlantic Anomaly. These patches aren't static. They move, merge, split, and evolve over time, scales of years to decades. Their motion reflects changes in the flow patterns of liquid iron deep in the outer core. The outer core is a spherical shell of molten iron and nickel, heated from below by the solid inner core and from within by radioactive decay. This heat drives convection, creating rising plumes of hot metal and sinking currents of cooler metal. The Coriolis effect from Earth's rotation twists these flows into helical patterns, and the motion of the conductive iron generates magnetic fields through electromagnetic induction. This process, the geodynamo, is chaotic and turbulent. Small changes in heat flow, composition, or rotation rate can alter convection patterns, which in turn alter the magnetic field at Earth's surface. Reverse flux patches appear when these convection patterns create upwellings or downwellings that generate backward-pointing field components strong enough to dominate locally. Some researchers suspect reverse flux patches are connected to structures at the core mantle boundary. Seismic studies reveal massive anomalies at the base of the mantle, regions where seismic waves travel slower than expected, suggesting different composition or temperature. The largest of these anomalies sits beneath Africa, spanning thousands of kilometers and rising hundreds of kilometers above the core mantle boundary. This African, large, low-shear velocity province, as it's technically known, might influence heat flow from the core into the mantle above it, altering convection patterns and contributing to the South Atlantic Anomaly's formation. The connection between the African anomaly and the South Atlantic anomaly is speculative, but intriguing. If the large, low-shear velocity province blocks heat escape from certain regions of the core, the liquid iron beneath it might convect differently, creating unusual flow patterns that produce reverse flux patches. These patches would then weaken the magnetic field at the surface, creating the South Atlantic anomaly we observe. It's a hypothesis that links processes separated by thousands of kilometers of rock and metal, requiring coordination between geophysics, seismology, and geodynamics. Computer models of the geodynamo can reproduce reverse flux patches, at least qualitatively. Simulations running on supercomputers model the liquid iron outer core as a sphere of electrically conductive fluid, rotating and convecting in 3 dimensions. These simulations show that reverse flux patches are not abnormal. They're a natural consequence of the geodynamo's complexity. What the models struggle with is predicting when and where patches will form, how long they'll persist, and whether their presence indicates an impending excursion or reversal. The chaos model, one of the most sophisticated magnetic field models available, tracks Earth's field using satellite data and incorporates time variations at high resolution. Chaos shows reverse flux patches moving westward over time, drifting across the core mantle boundary at speeds of roughly 10 to 15 kilometers per year. This westward drift has been observed for decades and is thought to reflect the dominant flow direction in the outer core. But the patches don't all drift at the same speed or in the same direction, suggesting the underlying flows are more complicated than simple rotation. What makes reverse flux patches particularly interesting is their potential connection to geomagnetic reversals. During reversals, the magnetic field weakens globally, and multiple magnetic poles appear at various latitudes. These temporary poles are thought to be caused by reverse flux patches growing strong enough to compete with the main dipole field. If enough reverse flux patches emerge and persist, they can disrupt the dipole entirely, allowing the field to reorganize with reversed polarity. The South Atlantic Anomaly might be showing us the early stages of such a process. The expanding anomaly, the splitting into two lobes, the presence of reverse flux patches beneath it, all of these could be signs that the geodynamo is entering a more complex state, where quadrupole and octupole components are strengthening relative to the dipole. Whether this trend continues toward a full reversal, or stabilizes into a temporary excursion, or simply weakens before recovering remains unknown. What scientists do know is that the outer core doesn't operate in isolation. It interacts with the solid inner core below it and the rocky mantle above it. The inner core grows slowly as the outer core cools, releasing latent heat and light elements that drive convection. The mantle imposes thermal boundary conditions and in some regions may modulate heat flow through variations in thickness or composition. These interactions create feedback loops that can amplify or dampen changes in the geodynamo. One speculative idea is that the African Large Low Shear Velocity province is acting as a thermal blanket, insulating the core beneath it and creating a region where convection is suppressed. This suppressed convection could alter the magnetic field generation in that region, weakening the field and creating reverse flux patches. If true, this would link the South Atlantic Anomaly to mantle structure, suggesting that Earth's magnetic field is influenced not just by core dynamics, but by the entire interior structure of the planet. Another speculative angle involves core composition. The outer core is not pure iron. It contains lighter elements like sulfur, oxygen, and silicon dissolved in the molten metal. The exact proportions and distribution of these elements affect density, viscosity, and convection patterns. If compositional variations exist within the outer core, regions with different compositions might convect differently, potentially creating localized anomalies in the magnetic field. These ideas remain hypotheses constrained by the limitations of observing Earth's interior. We can't drill to the core. We can't sample the liquid iron directly. Everything we know comes from indirect measurements: seismic waves, magnetic fields, gravitational variations, heat flow estimates, and computer models. Reverse flux patches are real observed phenomena, but understanding exactly what they mean for Earth's magnetic future requires more data, better models, and probably a few decades of continued observation. Still, the patches are telling us something important. They're showing us that Earth's magnetic field is not a stable, unchanging feature, but a dynamic system driven by processes we're only beginning to understand. And as we try to understand those processes, another question emerges that captures public imagination more than any other. Could the poles actually swap positions? And if so, what would that mean for life on Earth? Part 7. The Pole Alignment Forecast. Coincidence or clue? 2026 might mark a moment that happens only a few times per millennium, when Earth's magnetic poles briefly share the same line of longitude. Models suggest that sometime this year, both the north and south magnetic poles could align along approximately 135 degrees west longitude. The North Pole, currently racing across the Arctic towards Siberia, and the South Pole, wandering off the coast of Antarctica, would find themselves on opposite sides of the planet along the same meridian. This alignment is temporary, lasting only as long as it takes the poles to drift past each other. But it's geometrically striking and rare enough to catch scientists' attention. Pole alignment doesn't mean the poles are swapping positions. It means they're lining up longitudinally while remaining in their respective hemispheres. Think of it as 2 points on opposite sides of a sphere moving so they momentarily share the same slice through the planet's axis. The alignment has no direct physical significance. It's a geometric curiosity, a snapshot of the poles' wandering paths that happens to create a symmetrical configuration. But geometric curiosities sometimes hint at deeper dynamics. The fact that both poles are moving rapidly enough to create this alignment suggests that whatever processes are driving their motion are active and energetic. Poles don't move quickly when the geodynamo is stable. They move quickly when the flow patterns in the outer core are undergoing significant changes. Historically, such alignments are poorly documented because precise pole tracking is a modern capability. Before satellites and global monitoring networks, pole positions were estimated from compass measurements at scattered locations, and the accuracy was limited. We know poles have wandered throughout history, and we can infer approximate positions from paleomagnetic data in rocks, but reconstructing exact configurations from centuries past is difficult. The alignment could affect the overall geometry of the magnetic field in subtle ways. Earth's field is approximately dipolar, but the dipole isn't perfectly aligned with Earth's rotation axis, and it isn't centered at Earth's center. The dipole is tilted and offset, creating asymmetries in field strength around the globe. When the magnetic poles align longitudinally, that asymmetry might shift slightly, potentially affecting the structure of the magnetosphere or the distribution of field strength at the surface. Some researchers speculate that alignment could influence the South Atlantic anomaly's behavior. If the pole's motion reflects broader reorganization of the field, and if that reorganization involves strengthening of higher-order multipole components, the anomaly might intensify or change shape as the alignment occurs. This is speculative, based more on geometric intuition than rigorous modeling, but it's worth monitoring. Navigation systems might require minor adjustments during and after the alignment. The World Magnetic Model assumes certain relationships between pole positions and field strength distributions. If those relationships shift, the model's predictions could drift slightly from reality, requiring recalibration. For most users, this would be invisible, handled automatically by software updates. But for applications requiring high precision like drilling operations or geological surveys, small errors can accumulate into significant problems. The alignment also raises questions about core dynamics. Why are both poles moving quickly right now? What flow patterns in the liquid iron outer core could produce simultaneous acceleration of pole motion in both hemispheres? One possibility is that a large-scale circulation pattern is developing, perhaps a strengthening of existing convection cells or the emergence of new ones. Another possibility is that the solid inner core is interacting with the outer core in ways that perturb the field globally. The inner core rotates slightly faster than the mantle, a phenomenon called superrotation, and this differential rotation creates shear at the boundary between the solid inner core and liquid outer core. Shear generates turbulence, and turbulence affects the geodynamo. If the inner core's rotation rate is changing even slightly, it could influence pole motion and field structure in both hemispheres simultaneously. Some speculative theories suggest the alignment might be coincidental timing rather than a unified phenomenon. Perhaps the North Pole's acceleration is driven by one set of core processes localized to the Northern Hemisphere, while the South Pole's motion is driven by entirely different processes in the Southern Hemisphere. The two happen to produce longitudinal alignment by chance, rather than coordination. Testing this idea requires detailed models of core convection that can separate Northern and Southern Hemisphere dynamics, and such models are computationally expensive and uncertain. Public fascination with pole alignment tends to outpace scientific understanding. Online discussions conflate alignment with reversal, imagining scenarios where the poles swap positions overnight, or where the alignment triggers catastrophic magnetic field collapse. These fears are unfounded. Alignment is a geometric configuration, not a physical transition. The poles remain in their respective hemispheres, the field remains protective, life continues unaffected. Still, the alignment matters as a data point. It's a measurable event happening during a period of rapid magnetic change, and comparing field measurements before, during, and after the alignment could reveal subtle effects that improve our understanding of core dynamics. Swarm satellites will be watching closely, tracking any shifts in field strength, direction, or structure that correlate with the pole's positions. If the alignment coincides with measurable changes in the South Atlantic Anomaly, that would be significant. It would suggest that pole motion and the anomaly are connected through processes operating on hemispheric or global scales, not just localized quirks of regional convection. Such a connection would constrain models of the geodynamo, ruling out scenarios where the anomaly is an isolated feature unrelated to broader field evolution. The alignment also serves as a reminder that Earth's magnetic field is dynamic on human timescales. We're not watching something that changes over millions of years. We're watching something that changes over years and decades, fast enough to measure, predict, and be surprised by. That dynamism is both fascinating and unsettling because it means the protective shield we've relied on throughout human history is not a fixed feature, but a fluid evolving system capable of surprising us. So, the poles align briefly, and we watch to see what, if anything, it means. But beneath that question lies a deeper one about the magnetic field's long-term behavior. Is this alignment part of a temporary fluctuation, or is it a signpost on the road towards something bigger, an excursion, or even a reversal that could reshape Earth's magnetic landscape for thousands of years? Part 8. Hypothesis Crossroads. Excursion versus reversal versus oscillation. Earth's magnetic field stands at a crossroads, and scientists can't agree on which path it's taking. One scenario is a geomagnetic excursion, a temporary disruption where the poles wander significantly, the field weakens, and the dipole structure becomes chaotic before eventually recovering without completing a full reversal. Excursions are like magnetic hiccups, brief periods of instability that last anywhere from a few hundred to a few thousand years before the field restabilizes in its original polarity. The Lachamp event, which occurred around 41,000 years ago, is the best documented example. During the Lachamp, the magnetic field strength dropped to about 25% of its current value, and the poles wandered toward the equator. Paleomagnetic records from volcanic rocks and sediment cores show the field was chaotic and weak, but it eventually recovered, and the poles returned to their normal positions without flipping. Another scenario is a full polarity reversal, where the magnetic north and south poles completely swap positions. Reversals take much longer than excursions, typically thousands of years, and involve a prolonged period of weakening and reorganization before the field settles into a new stable configuration with reversed polarity. The last full reversal, the Brunhes-Matuyama reversal, occurred about 780,000 years ago. Since then, Earth's field has maintained its current polarity, making the present configuration one of the longest stable periods in the geological record. A third scenario, less commonly discussed, involves oscillatory behavior. The geodynamo might be entering a mode where it cycles between stronger and weaker states without progressing toward excursion or reversal. Think of it as the magnetic equivalent of breathing, periods of expansion and contraction driven by variations in core convection. Some models suggest the outer core can support multiple stable flow states, and transitions between these states could produce observable changes in field strength and structure at the surface without fundamentally altering polarity. Distinguishing between these scenarios is difficult because we're observing the field in real time, trying to predict future behavior based on limited historical data. The geological record extends back millions of years, but its temporal resolution is coarse. Sediment cores and lava flows preserve snapshots of the magnetic field at intervals of centuries to millennia, not years or decades. High-resolution data from satellites has only existed since the 1,960 seconds, giving us about 60 years of continuous observations. That's barely a blink in geological time. The Lachamp event provides clues about what excursions look like. During the Lachamp, radiocarbon production in the atmosphere spiked because the weakened magnetic field allowed more cosmic rays to reach Earth. Tree rings from that period show elevated carbon 1,4 levels, and ice cores from Greenland and Antarctica record increased beryllium 10, another cosmogenic isotope produced by cosmic ray interactions. These isotopes serve as proxies for magnetic field strength, allowing scientists to reconstruct the timing and intensity of the Lachamp, even though no humans were around to measure it directly. If the current changes represent the early stages of an excursion, we'd expect to see similar patterns. Continued weakening of the dipole field, strengthening of higher-order multipole components, and increased pole wandering. The South Atlantic Anomaly's expansion and splitting might be precursors, localized weaknesses that eventually spread or coalesce into global field disruption. But excursions are rare, occurring perhaps once every few tens of thousands of years, so the odds of witnessing one starting in our lifetimes are low. Full reversals are even rarer, occurring roughly every few 100,000 years on average, though the interval between reversals is highly variable. Some reversals are separated by millions of years, others by tens of thousands. The mechanisms triggering reversals remain debated. One hypothesis suggests reversals occur when the geodynamo becomes too turbulent, with competing convection cells disrupting the main dipole until the field collapses and reforms with reversed polarity. Another hypothesis involves interactions between the outer core and the solid inner core, where changes in inner core growth rate or rotation speed destabilize the field. Oscillatory models propose that the geodynamo naturally fluctuates in strength over millennial timescales without requiring external triggers. Heat flow from the core varies as the inner core grows and as mantle convection redistributes heat at the core mantle boundary. These variations modulate convection intensity in the outer core, which in turn modulates magnetic field strength. If true, the current weakening might simply be the downswing of a long-term cycle that will eventually reverse and strengthen again. Testing these hypotheses requires models that can simulate the geodynamo over thousands of years, incorporating realistic core properties, mantle boundary conditions, and inner core growth. Such simulations are computationally intensive, requiring months of supercomputer time to model even simplified scenarios. Results are often ambiguous because small changes in initial conditions or model parameters can produce dramatically different outcomes. The geodynamo is a chaotic system, sensitive to perturbations, and predicting its long-term behavior is fundamentally challenging. What scientists do agree on is that the current state of the field is unusual by recent historical standards. The dipole moment, a measure of the field's overall strength, has been declining for the past 2,000 years. The South Atlantic Anomaly is growing and splitting. The North Magnetic Pole is moving faster than at any point in recorded history. Reverse flux patches beneath the anomaly are visible in satellite data. These changes suggest something significant is happening in the core, even if we can't yet determine whether that something leads to excursion, reversal, oscillation, or stabilization. Public discussions of these scenarios often err on the side of catastrophism, imagining worst-case outcomes where the field collapses entirely, leaving Earth exposed to lethal radiation. Such scenarios are not supported by the geological record. Life survived the Lachamp event. Life survived hundreds of previous reversals. The field weakens during transitions but doesn't disappear. Earth's atmosphere provides some shielding even without a magnetic field, as Venus demonstrates. Though Venus lacks a magnetic field entirely and has lost most of its water vapor to space over billions of years, the real concern isn't extinction but disruption. A prolonged period of weakened magnetic field would increase radiation exposure for satellites, astronauts, and high-altitude flights. Power grids would be more vulnerable to geomagnetically induced currents during solar storms. Navigation systems would require frequent recalibration. These are engineering and economic challenges. Serious, but not civilization-ending. So, Earth's magnetic field stands at a crossroads, and we watch to see which path it takes. But while scientists debate excursions and reversals, another conversation is happening, one driven less by data and more by fear, where the boundaries between legitimate speculation and outright conspiracy blur. Part 9. Conspiracies and Misinterpretations. Deconstructing the Noise. The internet loves a good magnetic apocalypse story, and Earth's current field behavior provides plenty of fuel. Search for magnetic pole reversal online, and you'll find a spectrum of content ranging from sober scientific analyses to breathless predictions of imminent doom. Some posts claim the poles will flip completely by 2030, triggering earthquakes, volcanic eruptions, tsunamis, and atmospheric collapse. Others suggest governments are hiding evidence of accelerating field collapse to prevent panic. Still others link pole movement to climate change, ancient prophecies, or extraterrestrial intervention. The common thread is urgency. Something terrible is happening, and mainstream science is either ignorant or complicit in covering it up. These narratives thrive on misunderstandings of how the magnetic field works and what reversals actually entail. Pole movement gets conflated with field collapse. Localized anomalies like the South Atlantic Anomaly get interpreted as signs of global failure. Gradual changes occurring over centuries get compressed into timelines of years or months to manufacture urgency. Let's address the most common misconceptions. First, the magnetic poles are not about to flip overnight. Reversals take thousands of years. The geological record is unambiguous on this point. Second, pole movement does not cause earthquakes or volcanic eruptions. The magnetic field is generated in the liquid outer core roughly 3,000 kilometers below the surface. Tectonic activity occurs in the crust and upper mantle driven by completely different processes. There is no physical mechanism linking magnetic pole positions to seismic or volcanic events. Third, the South Atlantic Anomaly is not a hole in the magnetic field. It's a region of weakened field strength, but the field still exists there. Satellites crossing the anomaly experience higher radiation doses, but humans on the ground are protected by Earth's atmosphere, which blocks most charged particles regardless of magnetic field strength. Claims that the anomaly will expose South America to lethal radiation are unfounded. Fourth, the magnetic field has not been steadily weakening for millennia. It has fluctuated. The current decline in dipole moment is significant, but not unprecedented. Paleomagnetic data shows the field has been stronger and weaker at various points in the past, without triggering catastrophic consequences. So where do these misconceptions come from? Part of the problem is the seductive appeal of catastrophe narratives. Humans are pattern seekers, wired to detect threats, and magnetic field changes fit the profile of a slow-motion disaster, invisible, planetary in scale, and outside individual control. Add the fact that the magnetic field is genuinely important for protecting technology and astronauts, and you have ingredients for compelling but misleading stories. Another factor is the difficulty of communicating scientific uncertainty. Scientists hedge their statements because the data doesn't support confident predictions about whether an excursion or reversal is imminent. This hedging gets interpreted as evasion or incompetence. If scientists can't definitively rule out a reversal, conspiracy-minded audiences assume the worst-case scenario is likely or even certain. Media coverage sometimes amplifies the problem. Headlines prioritize drama over accuracy, turning magnetic field showing interesting changes into Earth's shield collapsing. Articles quote scientists discussing possibilities without clearly distinguishing low-probability scenarios from likely outcomes. Readers come away with the impression that danger is imminent when scientists are actually expressing measured curiosity and professional caution. Social media accelerates the distortion exponentially. Viral posts cherry-pick dramatic quotes or data points, stripping away context and nuance. Algorithms prioritize engagement over accuracy, and fear-inducing content generates engagement. So, the most extreme interpretations spread fastest, while truth struggles to keep pace. Corrections and clarifications struggle to gain traction because they're less emotionally resonant than the original claims. Historical precedents get misused in these narratives. The Carrington event of 1859, a massive geomagnetic storm that disrupted telegraph systems worldwide, is frequently cited as evidence that solar activity plus a weakening field could devastate modern civilization. The Carrington event was indeed severe, probably the most powerful geomagnetic storm in recorded history, but it occurred when the magnetic field was stronger than it is now. The storm's intensity was driven by an unusually powerful coronal mass ejection, not by field weakness. Modern infrastructure is more vulnerable because we depend on technology the Victorians didn't have, not because the field is weaker. Conspiracy theories often invoke government secrecy as an explanatory mechanism. If magnetic field collapse is imminent, why aren't authorities warning the public? The lack of warnings gets interpreted as evidence of cover-up, rather than evidence that the threat isn't imminent. This reasoning is circular. The absence of official concern proves there's something to be concerned about, and any official reassurance proves they're hiding the truth. Some theories borrow language from legitimate science to lend credibility. References to the South Atlantic Anomaly, reverse flux patches, and geomagnetic excursions appear in conspiracy content alongside claims about hidden government research or suppressed data. The mixing of real terminology with speculation makes it harder for non-experts to distinguish fact from fiction. The psychological appeal of these narratives shouldn't be underestimated. They offer simple explanations for complex phenomena, assign agency to impersonal processes, and provide a sense of insight and knowledge that makes believers feel informed while the masses remain ignorant. These narratives also externalize anxiety, channeling diffuse worries about technology dependence, environmental change, and geopolitical instability into a single concrete threat. Debunking doesn't always help because belief in these narratives often isn't based primarily on evidence. Presenting contradictory data or explaining geological timescales can be interpreted as further proof of cover-up. Effective counter-narratives need to acknowledge legitimate concerns, validating the real ways magnetic field changes affect satellites and technology, while clearly distinguishing those issues from exaggerated or imaginary threats. Scientists themselves bear some responsibility for communication gaps. Geophysics is a complex field with specialized jargon and mathematical models that are difficult to translate into accessible language. When scientists discuss uncertainties or competing hypotheses, they're demonstrating intellectual honesty. But to audiences unfamiliar with scientific norms, it can sound like confusion or disagreement that undermines credibility. The truth is less dramatic than either catastrophe narratives or conspiracy theories suggest. Earth's magnetic field is changing in measurable, interesting ways. Those changes have real technological implications. Scientists are monitoring closely but don't see evidence of imminent catastrophic failure. The field has survived hundreds of reversals over geological time, and there's no reason to think the current changes are fundamentally different from past fluctuations. This doesn't mean we should be complacent. Continued monitoring is essential. Improving models of core dynamics could help predict whether the field is entering an excursion or stabilizing. Hardening infrastructure against geomagnetic storms and radiation makes sense regardless of long-term field behavior. But panic and conspiracy serve no one. While humans debate what the magnetic field is doing and why, the universe continues its indifferent operation. Earth's magnetic peculiarities, significant as they seem to us, are minor variations in a cosmos filled with far more extreme examples of magnetism, radiation, and planetary physics. To understand our planet's field, it helps to step back and consider the broader context of magnetospheres across the solar system and beyond. Part 10. Broader cosmic perspective. Are we unique? Earth's magnetic field problems seem less urgent when you consider that Mars lost its entire magnetosphere billions of years ago. Mars once had a global magnetic field similar to Earth's, generated by convection in a liquid iron core. We know this because ancient Martian rocks preserve magnetization from that early field, frozen in place when volcanic lava cooled more than 4 billion years ago. Sometime around 3.5 billion years ago, Mars's dynamo shut down. The core cooled enough that convection stopped, and without convection, no magnetic field. The loss was catastrophic for Mars's atmosphere. Without a magnetosphere to deflect solar wind, charged particles from the sun began stripping away atmospheric molecules. Over billions of years, Mars lost most of its atmosphere, transforming from a world that might have supported liquid water on its surface into the cold, dry desert we observe today. The lesson from Mars is stark. Magnetospheres matter. They're not optional accessories for rocky planets. They're critical infrastructure that protects atmospheres from erosion by stellar winds and cosmic radiation. Earth's magnetic field has been performing this function for at least 5 billion years, probably longer, and it's one of the reasons life could evolve and persist on our planet's surface. Jupiter offers a contrasting example, an exercise in magnetospheric excess. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, generated by convection in a layer of metallic hydrogen deep inside the planet. This immense field creates a magnetosphere so large it would appear several times the size of the full moon if we could see it from Earth. Jupiter's radiation belts are correspondingly intense, filled with particles accelerated to near relativistic speeds. Any spacecraft venturing close to Jupiter must be heavily shielded, and even then, electronics degrade rapidly from radiation exposure. If Earth's South Atlantic Anomaly is a troublesome weak spot, Jupiter's entire magnetosphere is a weapon-grade radiation hazard. Mercury, the smallest terrestrial planet, has a weak but stable magnetic field generated by its partially liquid core. Mercury's field is only about 1% the strength of Earth's, barely strong enough to deflect the solar wind, which is far more intense at Mercury's orbital distance. The weak field creates a compact magnetosphere that hugs the planet closely, offering minimal protection. Yet, Mercury retains a thin atmosphere, suggesting that even weak magnetic fields provide some benefit, or that other factors like low gravity and proximity to the Sun dominate atmospheric evolution there. Venus has no global magnetic field at all. Its core may be entirely solid, or convection may be too weak to generate a dynamo. Without a magnetosphere, Venus's upper atmosphere is directly exposed to the solar wind, and ions are constantly being stripped away. Over billions of years, this process has contributed to Venus's hostile environment, though Venus's thick carbon dioxide atmosphere and extreme greenhouse effect are primarily responsible for its current state. Still, the absence of a magnetic field likely accelerated atmospheric loss early in Venus's history. These planetary comparisons highlight how unusual Earth's situation is. We have a strong, stable magnetic field that has persisted for billions of years, protecting a life-sustaining atmosphere. Mars had this once and lost it. Venus never maintained it. Mercury's is marginal. Only Earth has threaded the needle, maintaining the right combination of core heat, liquid iron, and rotational energy to keep the geodynamo running. The question of habitability extends beyond our solar system. Exoplanet studies, focused mostly on detecting planets and characterizing their atmospheres, are beginning to consider magnetospheres as habitability factors. A rocky planet in the habitable zone of its star might seem promising, but without a magnetic field, stellar winds could strip its atmosphere over geological timescales, rendering it uninhabitable despite ideal temperatures. Detecting exoplanet magnetospheres is extraordinarily difficult. Earth's magnetosphere would be nearly impossible to detect from interstellar distances with current technology. Indirect methods like searching for auroral emissions in radio wavelengths or observing how stellar winds interact with planets during transits offer possibilities, but results remain tentative. Some exoplanets orbit close to their host stars, experiencing stellar winds far more intense than anything in our solar system. These planets, called hot Jupiters, are bathed in radiation and charged particles. If they have magnetic fields, those fields must be correspondingly strong to provide any protection. If they lack fields, their atmospheres are likely eroding rapidly, potentially creating trails of escaping gas that could be observable. Earth's magnetic field also plays a role in cosmic ray protection. Cosmic rays are high-energy particles, mostly protons, accelerated by supernova explosions and other energetic events throughout the galaxy. When these particles reach Earth, the magnetosphere deflects many of them, reducing the radiation dose at the surface. During periods of weak magnetic field, like the Lachamp event, cosmic ray flux increases measurably. Ice cores show elevated cosmogenic isotope production during the Lachamp, confirming that more cosmic rays penetrated the atmosphere. The biological consequences of increased cosmic ray exposure are unclear. Some researchers have speculated that cosmic ray-induced mutations could accelerate evolution during periods of weak magnetic field. Though evidence for this is limited, what is clear is that technological systems are more vulnerable. Cosmic rays can cause single-event upsets in electronics, similar to the effects of trapped radiation in the Van Allen belts. More cosmic rays reaching the surface means more potential disruptions for ground-based electronics. Not enough to be catastrophic, but enough to be statistically significant. Comparing Earth to other planets also raises uncomfortable questions about long-term stability. If Mars's dynamo shut down, could Earth's eventually do the same? The answer depends on how quickly Earth's core is cooling. The geodynamo requires heat flow from the core to drive convection, and that heat flow depends on the temperature difference between the core and the mantle. As the core cools, the temperature difference shrinks, reducing convection intensity and eventually shutting down the dynamo. Current estimates suggest Earth's core is cooling slowly enough that the geodynamo should continue for at least another billion years, possibly much longer. But estimates depend on uncertain parameters like core composition, mantle viscosity, and heat production from radioactive decay. Small changes in these parameters could significantly alter the timeline. The broader cosmic perspective reminds us that magnetic fields are not guarantees. They're emergent phenomena arising from specific conditions, and those conditions can change. Earth has been fortunate maintaining its geodynamo for billions of years while Mars and Venus lost theirs. But luck isn't strategy, and understanding the processes that sustain our field is critical if we hope to predict its future behavior. As we zoom back from the cosmic scale to our own planet, the past year has brought discoveries that reshape our understanding of the universe, from distant galaxies to the Sun itself. These breakthroughs don't directly explain Earth's magnetic anomalies, but they expand the context in which we think about planetary physics, stellar activity, and the dynamic processes shaping worlds across the cosmos. Part 11. Astronomy's Big Week, the 2026 Super Bowl of Discovery. January 2026 has been exceptional for astronomy, a convergence of discoveries that happens maybe once a decade. The American Astronomical Society's winter meeting held earlier this month served as a launchpad for announcements that are still reverberating through the scientific community. The James Webb Space Telescope, now in its fourth year of operations, continues delivering images and spectra that challenge assumptions about galaxy formation. Recent observations of galaxies formed less than 500 million years after the Big Bang show unexpected levels of star formation activity. These galaxies are brighter and more massive than models predicted, suggesting either that early star formation was more efficient than thought, or that our understanding of galaxy assembly needs revision. One particularly striking discovery involves a galaxy cluster observed when the universe was only about 1 billion years old. Clusters this massive weren't supposed to exist that early. Galaxy formation models predict that small galaxies form first, then gradually merge into larger structures over billions of years. But this cluster appears to have assembled far faster than models allow, implying either rapid mergers or some unknown mechanism accelerating structure formation in the early universe. The implications ripple through cosmology. If galaxies and clusters formed faster than predicted, that constrains theories of dark matter distribution and the role of dark energy in cosmic evolution. It also raises questions about the initial conditions of the universe, the density fluctuations seeded by inflation, and how those fluctuations grew into the structures we see today. ALMA, the Atacama Large Millimeter Array in Chile, contributed its own discoveries related to planet formation. High-resolution observations of protoplanetary disks around young stars reveal intricate structures, gaps, rings, spirals, and asymmetries. These features are thought to be carved by forming planets whose gravity perturbs the disk material. By studying disk structures, astronomers can infer the presence and properties of planets that are too small or faint to detect directly. One disk observation showed a gap at a distance from the star roughly equivalent to Jupiter's orbit in our solar system. The gap's width and depth suggest a planet with several Jupiter masses is forming there, clearing out a channel in the disk as it grows. This supports models of gas giant formation via core accretion, where a solid core grows by accumulating dust and ice until it's massive enough to gravitationally capture hydrogen and helium from the surrounding disk. These observations inform our understanding of solar system formation, including the early history of our own sun and planets. The sun formed about 4.6 billion years ago from a collapsing molecular cloud. A disk of gas and dust surrounded the young sun, and within that disk, planets coalesced through collisions and gravitational interactions. Studying similar disks around other stars provides snapshots of this process at different stages. Solar activity is also relevant. Young stars are more active than the sun, producing frequent flares and ejecting streams of charged particles. If planets form while the star is highly active, their early atmospheres could be stripped away or altered by stellar wind and radiation. This has implications for habitability and atmospheric evolution, including Earth's early history when the sun was younger and more volatile. Telescope technology is advancing rapidly. The James Webb Space Telescope, with its infrared capabilities, complements ground-based optical and radio telescopes. Next-generation instruments, like the extremely large telescope under construction in Chile, will push observational limits even further. These telescopes will be able to directly image exoplanets in the habitable zones of nearby stars, analyze their atmospheres for biosignatures, and search for signs of magnetic fields or auroral activity. Exoplanet surveys are entering a golden age. Thousands of planets have been discovered using transit and radial velocity methods, and many more await confirmation. The diversity of these planets challenges our solar system-centric assumptions. Hot Jupiters orbiting close to their stars, super-Earths with no analog in our system, planets in tightly packed multi-planet systems. All of these expand our understanding of what planetary systems can look like. Some of these discoveries have unexpected connections to Earth's magnetic field. Understanding how stellar activity affects planetary magnetospheres helps contextualize Earth's interactions with the solar wind. If young sun-like stars are highly active, planets around them must either have strong magnetic fields to survive the bombardment or lose their atmospheres early. Earth's magnetosphere has been defending against solar wind for billions of years, but in the early solar system, that wind was likely stronger and more variable. The American Astronomical Society meeting also highlighted the role of artificial intelligence in astronomy. Machine learning algorithms are now being trained to identify galaxies, classify stars, and detect transient events like supernovae or gamma-ray bursts in massive datasets. These AI systems can process data far faster than humans, enabling discoveries that would be impossible through manual analysis alone. AI's role extends to space weather prediction, a field directly relevant to Earth's magnetic field challenges. By training neural networks on decades of solar wind data, scientists are improving forecasts of geomagnetic storms and their impacts on satellites and infrastructure. These models don't replace physics-based simulations, but complement them, offering faster predictions that can guide operational decisions. The convergence of telescope observations, AI analysis, and theoretical modeling is creating a feedback loop where discoveries drive new questions and new instruments answer those questions while raising even more. It's an exciting time to study the cosmos, but also humbling because each answer reveals how much we still don't understand. While astronomers peer into distant galaxies, others are studying galaxy clusters closer to home, cosmologically speaking, and finding those clusters are hotter than they should be, a discovery that challenges models of how structure grows in the universe. Part 12. Extremely hot ancient galaxy clusters rewrite cosmic growth models. Galaxy clusters are the largest gravitationally bound structures in the universe, and some of them are inexplicably hot. Clusters contain hundreds or thousands of galaxies, all orbiting a common center of mass held together by gravity. But galaxies make up only a small fraction of a cluster's mass. Most of the visible mass is hot gas, plasma heated to tens of millions of degrees, radiating X-rays that we can detect from Earth. This intracluster medium fills the space between galaxies, and its temperature tells us about the cluster's formation history. Recent observations of ancient galaxy clusters, clusters that formed when the universe was less than half its current age, show temperatures higher than models predict. These clusters are too hot for their age. Standard models assume that clusters grow gradually through mergers, with smaller clusters colliding and combining over billions of years. Each merger heats the intracluster gas through shocks and compression. Young clusters should be cooler because they haven't experienced as many mergers yet. But observations show some young clusters are as hot as older, more evolved ones. One possible explanation is that these clusters formed through unusually energetic mergers early in their history. If two massive clusters collided rapidly, the resulting shock could heat the gas to extreme temperatures. but this requires precise timing and specific merger configurations, which should be rare. Finding multiple examples suggests something more systematic is happening. Another explanation involves black holes. Most large galaxies contain supermassive black holes at their centers, millions or billions of times the mass of the Sun. These black holes occasionally feed on surrounding gas, releasing enormous amounts of energy in the process. Some of this energy heats the surrounding intracluster medium. If early clusters contained particularly active black holes, they could have injected enough energy to heat the gas beyond what mergers alone would produce. A third possibility involves dark matter, the invisible substance that makes up most of the universe's mass. Dark matter doesn't emit light, but its gravitational effects shape galaxy and cluster formation. If dark matter has properties we don't fully understand, such as interactions beyond gravity, it could affect how clusters form and how gas heats within them. These hot clusters challenge our understanding of structure formation in the universe. The current cosmological model, called lambda CDM, describes how the universe evolved from a smooth, hot state shortly after the Big Bang to the lumpy, structured state we see today. Dark matter clumps first forming gravitational wells that attract ordinary matter. Gas falls into these wells, heats up and forms stars and galaxies. Over time, gravity assembles these galaxies into clusters. Lambda CDM has been remarkably successful, predicting the cosmic microwave background structure, the distribution of galaxies on large scales, and the timing of structure formation. But it's not perfect. Discrepancies exist between predictions and observations, particularly on small scales. The hot cluster observations add to these discrepancies, suggesting we might be missing some aspect of structure formation physics. Magnetic fields in clusters might play a role. The intracluster medium is magnetized with field strengths measured in microgauss, millions of times weaker than Earth's field, but significant over cluster-wide scales. These fields can affect gas dynamics, influencing how shocks propagate during mergers and how energy is distributed. If magnetic fields are stronger in young clusters than models assume, they could contribute to the unexpected heating. Cosmologists are also considering whether early clusters experience different environmental conditions. The universe was denser and hotter in the past, and cosmic radiation backgrounds were stronger. If these conditions affected gas cooling rates or star formation efficiency, they might explain why young clusters are hotter than expected. Observationally, studying ancient clusters requires X-ray telescopes capable of detecting faint, distant sources. Current missions like Chandra X-ray Observatory and XMM Newton have provided most of the data, but their sensitivity is limited. Next-generation X-ray telescopes currently in planning stages will be able to study hot clusters in greater detail, measuring temperature profiles, density distributions, and compositional variations. Spectroscopy is key. By analyzing X-ray spectra from cluster gas, astronomers can measure temperatures, determine metal abundances, and even infer the history of stellar evolution within the cluster. Metal-rich gas suggests many stars have formed and died, enriching the intracluster medium with heavy elements. Metal-poor gas suggests a younger cluster with less stellar history. These observations connect back to Earth in subtle ways. Understanding how magnetic fields behave in extreme astrophysical environments informs our models of planetary magnetospheres. Clusters and planets operate on vastly different scales, but both involve magnetized plasmas, shock waves, and energy transport through fields. Insights from one domain often illuminate the other. The hot cluster mystery also reminds us that the universe still surprises us. Cosmology is often portrayed as a solved field, with lambda CDM providing a complete picture of cosmic evolution. But discoveries like unexpectedly hot clusters reveal gaps in our understanding, places where models need refinement or where new physics might be required. As astronomers grapple with distant galaxy clusters closer to home, artificial intelligence is revolutionizing how we predict space weather, offering tools that could help protect Earth's technological infrastructure from the solar storms that our weakening magnetic field makes more dangerous. Part 13. AI meets space weather. Prediction gets a huge upgrade. Predicting solar storms is about to get significantly better thanks to artificial intelligence learning from decades of space weather data. Traditional space weather forecasting relies on physics-based models that simulate the sun's magnetic field, solar wind propagation, and magnetosphere dynamics. These models work reasonably well, but have limitations. They require detailed knowledge of initial conditions like the magnetic field structure in a coronal mass ejection, and they struggle with the chaotic, non-linear interactions that occur when solar wind slams into Earth's magnetosphere. Predictions are often uncertain, with error bars spanning hours or days for storm arrival times and factors of 2 or more for intensity. Artificial intelligence offers a different approach. Instead of explicitly modeling the physics, machine learning algorithms learn patterns from historical data, feed a neural network decades of solar wind measurements, magnetosphere observations, and geomagnetic storm records, and it can learn to recognize precursor signals that indicate an incoming storm. These AI models don't understand the physics in the way humans do, but they can identify correlations and patterns that humans might miss. Recent advances have produced AI models that predict geomagnetic storm intensity and arrival time more accurately than traditional physics-based models in some scenarios. These models ingest data from solar observatories, solar wind monitors, and ground-based magnetometers, then output probabilistic forecasts of storm severity and timing. The forecasts update continuously as new data arrives, refining predictions in real time. One particularly successful application is predicting the KP index, a measure of geomagnetic activity derived from magnetometer readings at stations worldwide. The KP index ranges from 0, quiet conditions, to 9, severe storm, and it's used by satellite operators, power grid managers, and airlines to assess risk. AI models trained on historical KP data can predict index values several hours in advance, with accuracy comparable to or better than human forecasters. Another application is predicting single-event upsets in satellites by combining solar wind forecasts with satellite telemetry data. AI systems can estimate the probability of radiation-induced errors during specific time windows. This allows operators to preemptively shut down vulnerable systems or switch to backup hardware before crossing high-risk zones like the South Atlantic Anomaly during geomagnetic storms. The real power of AI comes from its ability to integrate diverse data sources. A human forecaster might monitor solar observations, solar wind speed, magnetometer readings, and historical storm patterns, synthesizing this information mentally. An AI can process all of these simultaneously, plus additional data streams like cosmic ray detectors, ionospheric measurements, and satellite anomaly reports, identifying subtle correlations that improve predictions. AI models are also being trained to predict solar flares, the explosive releases of energy from the sun's surface that often precede coronal mass ejections. Flare prediction is notoriously difficult because the sun's magnetic field is complex and constantly evolving. Machine learning algorithms analyze sunspot configurations, magnetic field topology, and historical flare data to identify active regions likely to produce significant flares within the next 24 to 48 hours. These predictions aren't perfect. Solar flares and coronal mass ejections are inherently chaotic, and no model can predict them with certainty days in advance. But even modest improvements in forecasting accuracy translate into real benefits. An extra hour of warning before a storm arrives gives satellite operators time to safeguard systems, power grid managers time to reconfigure networks, and airlines time to reroute flights. The South Atlantic Anomaly adds complexity to these predictions. AI models need to account for localized magnetic field weaknesses that amplify storm effects in certain regions. Some advanced models incorporate magnetic field maps derived from satellite data, using them to estimate how storm particles will interact with the anomaly's geometry. This allows more targeted warnings for satellites or spacecraft crossing the anomaly during storm periods. AI is also accelerating data analysis. Solar observatories generate terabytes of images and spectra daily, far more than humans can analyze manually. Machine learning algorithms can automatically identify coronal holes, filaments, sunspots, and flares in these images, flagging features of interest for human review. This automation frees scientists to focus on interpretation rather than data processing. Limitations remain. AI models are only as good as their training data, and space weather records extend back only a few decades. Rare extreme events like the Carrington event are underrepresented in the data, making it hard for models to learn about worst-case scenarios. Models also risk overfitting, learning noise, or artifacts in the training data that don't generalize to new situations. Hybrid approaches combining AI and physics-based models are showing promise. These systems use physics models to simulate the broad outlines of solar, wind, and magnetosphere behavior, then apply machine learning to refine predictions based on observational data. The combination leverages the strengths of both approaches. Physics provides understanding and extrapolation, while AI provides pattern recognition and data integration. Operational forecasting centers, like NOAA's Space Weather Prediction Center, are beginning to integrate AI tools into their workflows. These tools assist human forecasters, highlighting potential threats and suggesting forecast adjustments, but humans retain final decision-making authority. This human-in-the-loop approach balances automation speed and AI's pattern recognition with human judgment and domain expertise. The convergence of AI and space weather forecasting is timely. As solar activity peaks during the current solar maximum, and as Earth's magnetic field shows signs of instability, better predictions become increasingly valuable. Protecting the technological infrastructure that modern civilization depends on requires knowing when storms are coming and how severe they'll be. AI is making those predictions better, faster, and more reliable. While AI helps us predict space weather, the sun itself continues to surprise us with phenomena that challenge our understanding of how stars work, including recent observations of waves that might finally explain one of solar physics' oldest mysteries. Part 14. Solar Physics Breakthrough. Waves that might heat the corona. The sun's corona is inexplicably hot, and torsional Alfvén waves might finally explain why. The corona is the sun's outermost atmosphere, visible during total solar eclipses as a shimmering halo of plasma extending millions of kilometers into space. Temperatures in the corona reach 1 to 2 million degrees Celsius, far hotter than the photosphere, the sun's visible surface, which is only about 5,500 degrees. This temperature inversion violates our intuition. Heat should flow from hot to cold, not from the relatively cool photosphere outward to the scorching corona. Something must be transporting energy upward and depositing it in the corona, but identifying that mechanism has frustrated physicists for decades. Recent observations from solar observatories have detected torsional Alfvén waves propagating through the solar atmosphere. Alfvén waves are a type of magnetohydrodynamic wave, oscillations in magnetized plasma, where magnetic field lines act like strings on a guitar, carrying energy through vibrations. Torsional Alfvén waves involve twisting motions where plasma rotates around magnetic field lines rather than oscillating along them. These waves originate in the photosphere generated by convective motions and magnetic field interactions. Once launched, they propagate upward along magnetic field lines into the chromosphere and corona. As they travel, they carry energy with them. If the waves dissipate in the corona, releasing their energy as heat, they could explain the temperature inversion. Observing Alfvén waves is challenging because they don't produce strong emissions or obvious signatures. Researchers detected them using high-resolution spectroscopy, measuring Doppler shifts in specific spectral lines that reveal plasma motions. By tracking these motions over time, they reconstructed the wave properties: frequency, amplitude, and propagation direction. The key question is whether the observed waves carry enough energy to heat the corona. Preliminary calculations suggest they do, at least in some regions. The wave energy flux, the amount of energy transported per unit area per unit time, is comparable to the energy needed to maintain coronal temperatures against radiative and conductive losses. But whether this energy is efficiently dissipated as heat remains unclear. Dissipation mechanisms are critical. If waves simply pass through the corona without losing energy, they can't heat it. Several processes could dissipate Alfvén waves. Resonant absorption occurs when wave frequencies match natural oscillation frequencies of magnetic structures, transferring energy to plasma motions that eventually thermalize. Phase mixing happens when waves propagating along neighboring field lines get out of sync, creating small-scale gradients that turbulence can dissipate. Nonlinear interactions allow waves to cascade energy to smaller scales, where viscosity and resistivity convert it to heat. Computer simulations are testing these mechanisms. High-resolution magnetohydrodynamic models simulate wave propagation in realistic coronal magnetic field configurations, tracking energy flow and dissipation. Results vary depending on assumptions about magnetic field geometry, plasma density, and turbulence levels, but many simulations show that torsional Alfvén waves can indeed heat the corona under plausible conditions. If correct, this would solve one of solar physics' longest-standing mysteries, but it also raises new questions. What determines where and when waves are generated in the photosphere? How do magnetic field geometry and plasma conditions in the chromosphere and corona affect wave propagation and dissipation? Can waves explain all of the coronal heating, or do other mechanisms contribute? Solar cycle variations might play a role. During solar maximum, the sun's magnetic field is more complex, with more active regions, sunspots, and magnetic loops. This complexity could affect wave generation and propagation, potentially altering coronal heating patterns. Observations comparing wave activity at different phases of the solar cycle could test these ideas. Coronal heating affects solar wind properties. The corona is the source of the solar wind, the stream of charged particles that flows outward from the sun and eventually reaches Earth. Hotter coronas produce faster solar winds with higher particle densities. Understanding coronal heating mechanisms thus connects directly to space weather and its effects on Earth's magnetosphere. The torsional Alfvén wave discovery also exemplifies how advanced instruments enable breakthroughs. The observations required telescopes with high spatial resolution capable of resolving features a few hundred kilometers across on the sun's surface, and high cadence capturing images every few seconds to track wave motions. Ground-based solar telescopes and space-based observatories, like the Solar Dynamics Observatory, provide these capabilities. Spectroscopy was equally important. By measuring Doppler shifts in multiple spectral lines sampling different heights in the solar atmosphere, researchers reconstructed three-dimensional wave motions. This technique, called spectropolarimetry, when combined with magnetic field measurements, is a powerful tool for diagnosing plasma conditions and dynamics. Future solar missions will build on these observations. The European Space Agency's Solar Orbiter, launched in 2020, carries instruments designed to study the Sun's poles and inner heliosphere, regions difficult to observe from Earth's orbital plane. Data from Solar Orbiter will reveal how solar wind and magnetic fields vary with latitude, providing context for understanding wave heating and corona dynamics. The connection to Earth's magnetic field might seem tenuous, but it's real. Solar wind originates in the corona, and coronal heating mechanisms determine wind properties. Those properties, in turn, determine how solar wind interacts with Earth's magnetosphere. If coronal heating varies over the solar cycle, solar wind variations follow, modulating geomagnetic storm frequency and intensity. Understanding the sun's behavior helps us predict Earth's space weather. As we unravel solar mysteries, another frontier is opening closer to home. Our solar system, it turns out, is far more crowded than we realized, and upcoming surveys are poised to discover millions of objects we never knew existed. Part 15. Solar System Census Explosion. LSST predictions of millions of new objects. The Vera Rubin Observatory is about to rewrite our census of the solar system, and the numbers are staggering. When the Legacy Survey of Space and Time begins full operations, expected later this year, the observatory's 8.4-meter telescope and 2-gigapixel camera will scan the entire southern sky every few nights, tracking objects as faint as 25th magnitude. This capability will reveal asteroids, comets, Kuiper belt objects, and other small bodies that current surveys miss. Predictions suggest the LSST will discover millions of new asteroids, potentially 10 million or more, compared to the roughly 1 million known today. We're talking about increasing our inventory of solar system objects by an order of magnitude, transforming our understanding of the cosmic neighborhood we inhabit from a rough sketch into a detailed portrait. Most of these discoveries will be main belt asteroids orbiting between Mars and Jupiter, small rocky bodies ranging from a few kilometers to tens of meters across. These asteroids are remnants of the solar system's formation, leftovers that never coalesced into planets. By cataloging them, astronomers can study the solar system's early history, learning about the conditions and processes that shaped planetary assembly. Each asteroid tells a story about the chaotic early days when planets were forming, when collisions were frequent and violent, when the architecture of our solar system was still being negotiated through gravitational interactions that scattered some objects and bound others into stable orbits. The size distribution of these asteroids matters scientifically. Large asteroids are relatively easy to find. They're bright enough to detect with modest telescopes, and most kilometer-sized objects in the main belt have already been catalogued. But smaller asteroids, those in the tens to hundreds of meters range, vastly outnumber their larger cousins. The size distribution follows a power law, meaning for every asteroid of a given size, there are many more smaller ones. LSST's sensitivity will finally reveal the small end of this distribution, testing theoretical models of how asteroids formed and evolved through collisions over billions of years. Some discoveries will be more exotic. Near-Earth objects, asteroids and comets, whose orbits bring them close to Earth, are of particular interest for planetary defense. The LSST will dramatically increase the completeness of the near-Earth object catalog, particularly for smaller objects in the tens to hundreds of meters size range. These are large enough to cause regional devastation if they impact Earth, but small enough to have evaded detection so far. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters across, yet it released energy equivalent to 500 kilotons of TNT, injuring over 1,000 people and damaging thousands of buildings. Objects 10 times that size remain undiscovered in our vicinity, invisible until LSST starts searching systematically. Congressional mandates require NASA to catalog 90% of near-Earth objects larger than 140 meters by the end of this decade. Current surveys have found perhaps 40% of objects in this size range. LSST will close that gap, not just meeting the mandate, but exceeding it, potentially cataloging 95% or more of hazardous objects. This completeness matters because planetary defense requires advanced warning. If we discover a threatening asteroid decades before potential impact, deflection missions become feasible. Discover it months before impact and options narrow dramatically. Comets are another target. The LSST's sensitivity and cadence will enable detection of faint, distant comets in the outer solar system, providing early warnings of new objects entering the inner solar system where they could potentially threaten Earth. Long-period comets, which spend most of their time in the distant Oort cloud and occasionally plunge sunward on highly elliptical orbits, are particularly difficult to predict because their orbits aren't well constrained until they approach the Sun. More complete comet catalogs improve predictions and reduce surprise encounters. Comets are especially dangerous because they approach from the outer solar system at high speeds, giving less warning time than asteroids in more predictable orbits. The distinction between asteroids and comets blurs at the boundaries. Some asteroids show comet-like activity when heated by the Sun, releasing gas and dust despite being primarily rocky. Some comets have exhausted their volatile ices and now resemble asteroids. LSST will discover many of these transitional objects, helping astronomers understand the continuum between rocky and icy bodies and how solar heating transforms comets over multiple orbits. The Kuiper Belt, the region beyond Neptune containing icy bodies and dwarf planets, will be extensively surveyed. Current catalogs contain only a few thousand Kuiper Belt objects, but estimates suggest tens of thousands await discovery. These objects preserve the solar system's primordial composition, frozen in time since formation. Studying their sizes, orbital properties, and compositional variations constrains models of planet migration and solar system evolution. The Kuiper Belt isn't just a collection of frozen rocks, it's an archive, a geological record written in ice and rock that documents conditions 4.5 billion years ago when the solar system was young. One particularly interesting question involves Neptune's migration. Models suggest Neptune formed closer to the Sun and migrated outward early in solar system history, scattering Kuiper Belt objects as it moved. Some objects were ejected entirely, becoming Oort cloud members or escaping the solar system. Others were captured into resonant orbits like Pluto, which orbits twice for every 3 Neptune orbits. By mapping the orbital distribution of Kuiper Belt objects, astronomers can test migration models and refine our understanding of how the outer solar system evolved. LSST might also detect objects with unusual orbits, retrograde asteroids orbiting opposite to the planets, objects on extremely inclined or eccentric orbits, or even interstellar visitors passing through the solar system like Oumuamua and Comet Borisov. These rare objects provide unique insights into dynamical processes and compositional diversity. Retrograde asteroids are particularly puzzling. Most solar system objects orbit in the same direction the planets do, a consequence of forming from a rotating disk. Retrograde objects must have been perturbed by gravitational interactions or captured from outside the solar system, and finding more examples will help identify which mechanisms dominate. Interstellar objects are particularly intriguing. Oumuamua, discovered in 2017, was the first confirmed interstellar object detected passing through the solar system. Its unusual shape, reflectivity, and acceleration generated debate about its nature and origin. Comet Borisov, detected in 2019, appeared more conventionally comet-like, but still raised questions about comet formation in other planetary systems. LSST's wide field of view and frequent cadence make it well-suited to detect more interstellar visitors, potentially several per year, once the survey is fully operational. Each interstellar object is a sample from another star system carrying information about planetary formation, conditions around stars with different masses, compositions, and ages. The scientific value of detecting multiple interstellar objects is immense. With only 2 examples so far, we can't determine whether Oumuamua's oddness represents typical interstellar objects or an outlier. More detections will reveal the distribution of shapes, sizes, compositions, and trajectories, constraining models of how planetary systems eject material into interstellar space. Some models predict interstellar space is filled with planet-sized rogues ejected during planetary system formation. LSST won't detect those, but it might find smaller fragments, pieces of shattered worlds drifting between stars. The data volume will be immense. LSST will generate tens of terabytes of data each night, requiring automated pipelines to process images, detect moving objects, link observations into orbits, and alert astronomers to interesting discoveries. Machine learning plays a crucial role here, classifying objects, filtering false detections, and prioritizing targets for follow-up observations. Neural networks trained on simulated asteroid detections can distinguish real objects from cosmic ray hits, satellite trails, and image artifacts that plague automated surveys. These AI systems will need to operate with minimal human supervision, making decisions about which detections warrant alerts and which can be catalogued without immediate follow-up. One challenge is computational. Linking observations into orbits requires comparing positions from multiple images taken over days or weeks, a combinatorial problem that grows rapidly with the number of detections. Efficient algorithms and high-performance computing are essential. Another challenge is handling the deluge of alerts. When LSST detects something new or changing, it issues an alert within minutes. Thousands of alerts will be generated nightly, overwhelming astronomers unless automated systems triage them effectively. Community alert brokers, specialized software systems that filter and prioritize LSST alerts, are being developed by multiple teams to help astronomers navigate this data flood. The solar system census has implications beyond pure science. Asteroid mining companies, though currently more aspirational than operational, will benefit from detailed catalogs identifying resource-rich targets. Certain asteroids contain high concentrations of valuable metals like platinum and gold, while others are rich in water ice that could be processed into rocket fuel. Detailed surveys identifying these resource-rich targets could enable future space industrialization, though economic and technological barriers remain formidable. Planetary defense efforts require complete inventories of potentially hazardous objects. Knowing what's out there is the first step in protecting Earth from impacts. Once an object is catalogued, its orbit can be refined with additional observations, predicting close approaches decades or centuries in advance. Mission planners seeking targets for spacecraft flybys or sample returns will have vastly more options. Japan's Hayabusa missions and NASA's OSIRIS-REx successfully returned samples from asteroids, analyzing pristine solar system material in laboratories. LSST will identify thousands of accessible targets for future sample return missions. There's also a subtle connection to Earth's magnetic field and space weather. Dust and micrometeorites from asteroids and comets constantly rain onto Earth, adding material to the atmosphere and occasionally producing meteor showers. This material interacts with the upper atmosphere, contributing to ionization and affecting radio communications. During geomagnetic storms, when auroral activity intensifies, these interactions become more complex. Understanding the small body population helps quantify these contributions. Meteor showers occur when Earth passes through debris streams left by comets, and the timing and intensity of these showers depend on the distribution and evolution of that debris. The LSST represents a shift in astronomy from targeted observations of specific objects to broad surveys capturing everything above a detection threshold. This approach generates vast data sets that can be mined for multiple purposes, enabling discoveries that weren't the original survey goal. It's the astronomical equivalent of casting a wide net and sorting the catch afterward. Serendipitous discoveries often emerge from such surveys, phenomena nobody predicted, but that become obvious once comprehensive data exists. Completing the solar system census is a milestone in humanity's exploration of its cosmic neighborhood. For most of history, humans knew only the planets visible to the naked eye and a handful of asteroids. Telescopes expanded the inventory, but until recently, detection limits meant most small bodies remained invisible. LSST pushes those limits dramatically, revealing a solar system far more crowded and dynamic than we realized. This crowding has implications for understanding solar system evolution, planetary formation, and the delivery of water and organic molecules to early Earth. These millions of new objects won't directly affect Earth's magnetic field or solve the South Atlantic Anomaly's mysteries, but they enrich the context in which we understand our planet. Earth exists in a busy solar system, a dynamic environment shaped by gravitational interactions, collisions, and the sun's radiation. Understanding that environment, from the largest planets to the smallest asteroids, deepens our appreciation of the forces and processes that have shaped Earth over billions of years. And as we catalog the solar system, measure magnetic field changes, predict space weather with AI, and observe distant galaxies, a common thread emerges. The universe is not static. It's a dynamic, evolving system operating on timescales from milliseconds to billions of years. Earth's magnetic field is part of that system, subject to the same fundamental physics governing everything from the geodynamo in our core to the dynamos in distant exoplanets. We're learning that change is the only constant, whether we're watching the sun erupt, tracking asteroids, or monitoring the shield that protects us. The question isn't whether Earth's magnetic field will continue changing. It will. The geodynamo has been operating for billions of years, and it will continue operating, fluctuating between stronger and weaker states, occasionally producing excursions or reversals, eventually stabilizing in configurations we can't predict. What we can predict is that monitoring will continue. Satellites will track every shift, models will improve, and our understanding will deepen. The South Atlantic Anomaly is a window into Earth's interior, revealing processes occurring thousands of kilometers beneath our feet. Whether it leads to excursion, reversal, or temporary wobble, we'll be watching, measuring, learning, and adapting our technology to whatever changes come. That's the nature of living on a dynamic planet in a dynamic universe. Nothing stays the same forever,